This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we'll be getting into database scaling choices for my e-commerce platform, from single node to what I'd add at scale. Premature scaling is one of the most expensive forms of technical debt. You add a replica before you have a read problem. Now you have routing logic, replication lag monitoring, 2 connection pools, and your read-writes consistency problem to solve for a workload that a single well-tuned Postgres instance could have handled for another year. The counter failure is not scaling when you need to. It's connection exhaustion under moderate load because nobody thought about pooling. Slow queries that an index would fix for free while the team debates whether to add a caching layer. A primary node saturated with analytics queries that belong on a replica. The right approach is a scaling ladder, 6 rungs, each with a specific trigger metric, each adding a specific kind of capacity. Don't climb without this signal. This video is about what's on each rung and how to know when you've reached it. The scaling ladder. The 6-rung ladder from single node to horizontally distributed. The diagram shows the progression. Single node with proper indexes and query optimization. Connection pooling, vertical scaling, query caching, read replicas, horizontal partitioning or sharding. Each rung is a response to a specific measured bottleneck. Missing indexes cause sequential scans, measured with explain analyze. Connection exhaustion is measured by monitoring max connections and connection wait times. Working set not fitting in cache is measured by shared buffers hit rate. Read throughput exceeding primary capacity is measured by CPU utilization and query latency. Table sizing exceeding practical index performance is measured by query plans and storage growth. The cost of each rung also escalates. Fixing a missing index costs nothing and takes minutes. Adding a read replica costs infrastructure spend, adds replication lag to monitor, and introduces the read your writes routing problem. Scaling triggers. The triggers metrics in detail map to each rung. Query optimization trigger. Any query showing sequential scans on tables with more than 10,000 rows in explain analyze. This is free to fix with immediate improvement. Connection pooling trigger. Any connection exhaustion errors or connection wait time above 5 milliseconds. This is not optimal for serverless. It is a precondition for stability. Vertical scaling trigger. Shared buffers cache hit rate below 85% sustained. Adding RAM brings more of the working set into cache. A 100x read speed improvement for cache pages versus disk reads. Read replica trigger. Primary CPU sustained above 70% with the majority of queries being reads after query optimization and vertical scalings are exhausted. Table partitioning trigger. A single table above 50 gigabytes or query plans on time series data showing index scans that still cover millions of rows. The sharding trigger. Write throughput that a single primary node cannot sustain or data volume that exceeds a single node storage limit. This is the last resort. Sharding fundamentally changes your data model and is very difficult to reverse. Where I am now, single node, plenty of room. My current setup, Supabase hosted Postgres, single primary instance. Supabase manages backups, updates, and failover. I manage schema and query performance. I use the Supabase pull report for all application connections. PgBouncer in transaction mode. Connections are held only during active transactions and return to the pool immediately after commit. Cold starts don't exhaust the connection pool. My query monitoring workflow. Supabase's query log flags any query over 100 milliseconds. For anything flagged, I run explain analyze to identify the bottleneck. In 90% of cases, it's missing index or a n+1 query that's easy to fix. The right side shows Postgres capabilities. I'm relying on that infrastructure. What I'm relying on are not infrastructure additions. JSON-B engine for flexible content, TS vector for full text search, ACID transactions for financial operations, RLS for data isolation. These are features of a single node that I already have. Adding infrastructure doesn't make them better. It adds complexity around them. Connection pooling. Why serverless needs it. Postgres allocates a process per connection. Each connection costs approximately 5 to 10 megabytes of RAM. The default maximum is 100 connections on a standard installation. Without pooling, on a serverless platform, 100 concurrent Vercel functions invocations each open a database connection. All 100 are held for the duration of those requests. A traffic burst during a sale event spike that spikes the connection count. All 100 are held for the duration of those requests. A traffic burst during a sale event spikes the connection count. Now requests start failing with too many connections. User checkouts fail. This happens under moderate traffic. 100 concurrent users is not a high traffic scenario. The failure mode is silent until it isn't. P99 latency spikes first, then requests start returning errors. By the time you're investigating, real users are experiencing it. PgBouncer sits between your application and Postgres. It maintains a small pool of actual database connections, perhaps 10 to 20, and multiplexes many application connections through them. In transaction mode, a server connection is held only during an active transaction and returned to the pool between transactions. A serverless function that opens a connection, runs a query, and closes it releases the server connection back to the pool immediately. Supabase exposes PgBouncer on port 6543. The switch is a single connection string change. Port 5432 to port 6543. Use 6543 for all application connections. Use port 5432 only for migrations. PgBouncer in transaction mode does not support DDL statements reliably. Read replicas. Read replicas help with 4 specific workloads. Product catalog, blog posts, and search results are all reads. Route them to a replica and the primary handles only writes. Long-running analytic queries that would block primary operations can run on a dedicated analytics replica. Report generation, CSV exports, dashboards. They're expensive reads that benefit from isolations. Geographic replicas reduce latencies for users in distant regions. The read your write problems must be solved before adding replicas, not after. The scenario: a user purchases a license, the write lands on the primary, the user navigates to their downloads page. The read is routed to a replica. The replica is 200 milliseconds behind the primary. The user sees no license. They open a support ticket or initiate a chargeback. 2 solutions. Simple. After any write, route the same session's reads to the primary for 5 seconds. Most replication lag is well under 5 seconds under normal conditions. Architecturally correct. Track the write-ahead log sequence number at write time. Route to a replica only when the replica's reported LSN is at least equal to the write's LSN. This guarantees the replica has the specific write, not just that time has passed. I have no replicas today. This problem doesn't exist yet for me, but the routing solution must be designed and in place before adding the first replica, because the first replica is when the problem becomes real. Index design. The indexes I have today, every foreign key is indexed. Postgres doesn't create indexes on foreign keys automatically. My order, user ID, order items, order ID, order events, order ID, all have explicit indexes. Without these, querying all orders for a user requires a sequential scan of the entire orders table. Orders created at sending and orders created at orders events created at, or timestamp based ordering and pagination. Without these, order by created at sending limit 20 requires sorting the full table before applying the limit. A composite index on order events type created at descending for the query all payments failures in the last 24 hours. A composite index covers both conditions simultaneously. Without it, the database would use one index and then filter the other condition in memory. A GIN index on notes FTS for full text search. GIN is the correct index type for TS vector. It supports the double @ operator used in full text search query. Create index concurrently for all production table indexes. Plain create index takes an exclusive lock for the full build duration. Unacceptable on a live table. Concurrently takes a lighter lock at the start and the end and builds the index without blocking reads or writes. Query optimization before infrastructure. The workflow for any slow query: wrap it in, explain, analyze, buffers, format text, and read the output. 4 signals to look for. Sequential scan on large tables means a missing index. The database is reading every row. Nested loop on large row counts means the join order or join strategy is wrong. Adding an index on the join column often fixes it. The difference between the planner's row estimates an actual row process means statistics are stale. Analyze on that table refreshes them. Buffers showing many read operations and few hit operations means a low cache hit rate. The working set isn't fitting in shared buffers. 5 common fixes. N+1 queries. Load all related data in one query with a join or batch load with where ID equals any. Missing foreign key indexes. Select all. In production, select only the columns you need. Stale statistics. Missing sort index for order by with limit. A 5x query improvement is free and takes minutes. A read replica costs money per month, adds routing complexity, and introduces replication lag as a new failure mode to monitor. Fix the query first every time. Vertical scaling, adding more RAM and CPU to the primary node, is the most underrated option in scaling discussions. The reason: Postgres shared buffer cache. Frequently accessed data pages are cached in RAM. A read from shared buffers takes approximately 0.1 milliseconds. A read from disk takes 10 to 100 milliseconds. 100x difference. If your working set, the pages your queries access most frequently, fits in RAM, most query hits cache and are fast. The upgrade decision: if adding more RAM would bring the hot working set into cache and the cache hit rate is currently below 85%, vertical scaling is likely the right move. It's reversible. You can downgrade later. Doesn't add routing complexity. It doesn't introduce replication lag. And it's often cheaper than a read replica for the throughput improvement it delivers. The Supabase plan tiers: free for development, pro for production up to moderate traffic, pro with compute add-ons when P99 latency claims and the working set doesn't fix in Pro's default RAM. Read replica only after query optimization and vertical scaling are exhausted. What I'd add at scale: 4 additions with specific triggers, metrics, and explicit complexity cost. Read replica, triggered when primary CPU is sustained above 70% and the majority of queries are reads. What it enables: route catalog, blog, and search reads to the replica. Okay, so read replica, triggered when primary CPU is sustained above 70% and the majority of queries are reads. What it enables: route catalog, blog, and search reads on the replica. The costs: read your writes routing logic, lag monitoring, 2 connection pools to manage, dedicated connection pool or tuning, triggered when connection exhaustion errors occur or connection wait time exceeds 10 milliseconds P99. What it enables: precise pool sizing for the workload. The cost: pool sizing requires load testing, not guesswork. Table partitioning, triggered when a single table exceeds a 50 gigabyte or queries on order events remain slow despite indexes. What it enables: order events partition by created at range, so recent event queries hit one small partition. The cost: partition key choice is permanent. Changing it requires rebuilding the table. Dedicated analytics database, triggered when analytics queries are measurably impacted production latency. What it enables: it isolates heavy aggregations. The cost: an ETL pipeline to maintain and a consistency model to reason about between production and analytics data. Summary: scale when you have the signal, not before. The scaling ladder has 6 rungs with specific trigger metrics. Don't climb without the measurement. Premature scaling adds operational complexity with no performance benefit. Connection pooling via Supabase pooler port is essential for serverless. Direct connections exhaust max connections under moderate concurrent load. PgBouncer transaction mode for application connections. Direct port for migrations. Query optimization before infrastructure. Explain, analyze every slow query. A missing index fix is free and immediate. A read replica costs money, adds latency, and introduces read your writes routing complexity. Vertical scaling before horizontal. Doubling RAM can produce a 2 to 3x performance improvement at lower cost and 0 routing complexity. If the working set fits in cache, reads are 100 times faster. Read replicas require solving read your write before adding them, not after. A stale read after purchase produces support tickets and chargeback. Design the routing before adding the first replica. For a client, database scaling on this platform follows an explicit trigger-based ladder. Connection pooling is active via Supabase's PgBouncer pooler. Query performance is monitored via Supabase query logs with explain, analyze, run on any query over 100 milliseconds. Read replicas, vertical scaling, and partitioning each have defined trigger metrics and documented trade-offs. Some fleshed out thoughts. I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're designing database scaling for your own platform, connection pooling, index strategy, or the read replicas routing problem, reach out. I'm open to freelance projects and consult. The full post is linked in the description below. query optimization walkthrough, index decision guide, and the read replica routing implementation. Next in this series, observability, structured logging, SLOs, and what I'll add when traffic grows. I'll see you there.